All right, so as you can see from our intro, we're going to be talking about matrices. No, not the actual movie, but we are talking about matrix 4x4s, which are found everywhere in Houdini and in 3D. And we'll also be talking about other kinds of matrices as we go along. Right, so what exactly is a matrix? So ultimately, it's just basically a grid of numbers, right? So here we have a 4x4 matrix, and we will also very commonly come across 3x3. You do get others, you do get 2x2, but you also even get like a 4x2 or just whatever. Okay, it's basically just a grid of numbers. But the 3x3 and 4x4 are more common to come across, and they have very specific uses within 3D. So we're going to be talking mostly just about those two types. Okay, starting with the 4, because really the 4x4 includes the 3. So the 3 is just part of. There's one component missing in the 3x3. So we're gonna sort of start with the whole 4x4 matrix and then go from there. Now, what a matrix really is, very similar to when we were talking about quaternions in the previous lesson. It's kind of numbers that are not really user-friendly. They are not very easily usable, and we don't ever manually enter numbers into a matrix. Like, we don't just sit with this grid and kind of go and start changing these numbers manually. Okay, but they are sort of an interim function. So we will take the transformations of our character or our object, whatever we're doing, and then convert it or read it as a matrix. And then from that, we can extract certain information. We can run certain functions. There's a lot of really cool things that we can do with matrices, but we normally generate them from something, or we run other functions to maybe feed certain information into them in a way that is actually sort of understandable for us as humans. We can understand maybe just rotation around the y-axis or scale on z, but where do we enter those numbers into a matrix? Well, there is a very complicated kind of mathematical pattern of how those numbers get input into a matrix, and we are not going to be covering the maths behind it really, because there's no point. It's so far beyond, like, you never need to do it in Houdini, and so we're not going to be sort of looking at how to do it manually, but rather how to use what the tools that Houdini has in place for us to work with matrices. And then we want to try and understand what they are and what they do, just so that those functions make more sense. Okay, so ultimately, what happens with matrices, the primary use of them is for transformations. Okay, so our translate, our rotate, scale, and shear, as well as, of course, uniform scale and the offset of pivots. So those are really kind of all of those combined together form our matrix. So you can think of it as a bunch of numbers that really give you all the information about where a particular object exists in space. But not just its position, but its, how is it rotated? How is it scaled on different axes, as well as how is it scaled overall? And is it sheared on any particular planes as well? So all of that information embedded in these 16 numbers, so 4x4, okay? And then later I'll be talking about what happens with a 3x3 matrix and how that differs. Okay. So in this example, to stick with our matrix theme, I've got two little squid things here, the default Houdini geometry. And what I've got on the right-hand side, I've got a matrix, which we can enter numbers manually into it. Okay, as I said, we're not really ever going to do that, but I want to show you how these numbers kind of work and the weird relationship they have with one another. So I've got a matrix, which is going to alter our left-hand squid. But underneath him is the translate, rotate, scale, and shear values from this. So it's kind of the conversion of this matrix into these numbers. Okay, So then as we alter this matrix, we'll see what happens to these numbers and what happens to our squid. And then the guy on the right is controlled by these. So these are what we're used to seeing: translate, rotate, scale, and shear. Okay, well, I do not have a uniform scale in here, but that's because that is technically just a multiplier of the scale values coming in over here. So that is, it's not its own separate component of the matrix. It is just a multiplier of one of the input components. Okay, so this is what we're used to seeing. It's going to alter the guy on the right, and then it's going to show us the resulting matrix. So it's going to convert from these four sort of parameters to an actual matrix. Okay, and then we'll see how this kind of works. So let's start with the guy on the left. So I'm going to show you here, if we start just manipulating some of these numbers manually, you'll see kind of what happens, right? So I start scaling just this one number up, okay? And he has kind of done some weird scaling, okay? So in other words, he's basically sheared along the one axis, okay? So you'll see here that the shear value in this is exactly the same. But then now he's got some scale values, he's got some rotation values. And if I start altering other parameters, you see that then things start getting a bit wonky. Okay, because it's not like this number relates directly to just shear on the x, because then this 2.2 would be somewhere. Okay, and if we took this back down to 0, then you'll see that there is a 2.2 here. So if we only scale on one axis at a time, then yes, there seems to be a corresponding number. But as soon as we start adding additional shear on multiple channels, then these numbers kind of disappear from what we're seeing. Same thing would happen if I now start altering another number. Okay, so now none of our shear numbers at the bottom here are represented in any numbers here, and yet they were when they were isolated. Okay, same with our sort of scale, right? So you'll see some of these that start at 1 sort of, you know, they kind of relate to scale, sort of. I mean, if we maybe reset it, you'll see how if I scale just along one axis, this 2.2 here matches 2.2 there, but only when it's in isolation. Okay, so it's sort of got this weird relationship between these numbers where a lot of the time they seem to do just one thing. If you move them on their own, like translate here, we move along y, and it seems to move along y. But the more numbers we add up and sort of compound on top of one another, it's like these overlap. And it's because there's a ratio or a relationship between the, for example, translate x and then the scale x and so on. And that relationship is embedded in the way that these numbers are manipulated. Okay. Which is why it kind of means it becomes impossible for us to work with matrices manually. We rather work with these separate numbers, and then it embeds those numbers inside of this matrix. Now, I just want to point out, I'm sure you will have noticed here that a matrix here, this is a default matrix. So when I have no translations, no rotations, no scale, and no shear. But I just want to point out that no scale means 1, not 0. And you see how we know that instinctively, that translate to 0 is the default, but scale to 0 means it disappears completely, right? That's not correct. We would need to scale to 1 for that to be the default. And it's sort of the same in the matrix. You can see here that when it's all set to 0, that these are all also set to 0 and our object has disappeared. When they're set to 1, then he seems to be there. So these here almost seem to relate to x, y, and z scale. But like I said to you before, there is this kind of layering of, sure, we can scale along y and that number will match that number. But then when we start doing other things, we rotate, we translate, we shear, and then other numbers start to overlap and change things. Okay, so let's just reset all of these. Okay, so a default matrix is called an identity matrix. Okay, and there are even functions for it. You find in vops and vex, there's an identity. So in vops, you just create a constant and set it to matrix. In vex, you'll find an ident function, which creates an identity matrix. So that is basically an empty matrix, but by empty, it doesn't mean all zeros. It means this diagonal pattern of ones, and then everything else is set to 0. Very similar to how the defaults for translate, rotate, scale, and shear are not all zeros. In the scale channel, it's ones. Okay, so you can see here now how we, as we rotate, like let's do an example here. Let's take this guy, and if we rotate him -45 on Y, so you'll see that he's kind of rotating 45 degrees towards facing us. Now what's happened there is it actually manipulated multiple of these numbers to 0.71, which, I mean, how does that relate to -45, right? And it has to be, you'll see that because these numbers are all equal, except this one has a negative, it is now rotated on -45. If we make that positive, then the negative is here, not here, okay? So I'm sure you can sort of see that there's some relationship happening in here, but definitely not something that we could do manually. If we wanted to go do that and see these 4 are the ones that keep changing whenever we change Y rotation. So sure, we can go and change these 4 again. Now, remember also, I just want to point out that this one, and this one seemed to be related to our X, Y, and Z scale. But you'll see here, our scale hasn't changed, and we've rotated 45 degrees, and now suddenly these numbers are different. So as we decrease scale on X, yes, this number decreases as well, but it didn't even start at 1 because of our rotation. So there's like this weird internal relationship happening. So as I said, we can come here and we can start doing this. So this was -0.71. But you see, look at how this is sheared. So it has actually sheared along that angle. But if we then go and finish adding all these numbers, so then this one should be 0.71. Okay. So now it's sheared on a different axis, and then 0.71. And then the final one is also 0.71. And now it has rotated the same as this. What you'll notice is that the rotation, actually there is, like we've seen before, this number seems to kind of relate to scale when in isolation, and there also seems to be ones that relate directly to shear in isolation, but there doesn't seem to be rotation. None of these, when we alter it, does it seem to just rotate. Okay, there only seems to basically be scaling and shearing. But what happens is when you shear in one direction and then shear in another, it seems to move the points as though it has rotated. And that's kind of where this relationship comes up. So what we're really doing here is scaling on 2 axes and shearing on 2 axes. And so it's adding up to a rotation. Okay. Now you don't need to understand that really. Like you don't need to be able to replicate that manually. It's just important to see and understand why we can't work with matrices directly, but that they are storing within them, and by the sort of the relationship between multiple numbers, and it's like the sign of the whole column. So if there's one negative sign within a column and within a row, then that means something to that matrix. But it's ultimately 16 numbers that store all of this information for us in a very sort of interesting way. And when we start looking at the functions that we can do with matrices, you'll understand what it enables us to do. Also, don't forget that it's not only storing all 4 of these, but it's also storing the pivot location, the rotation of the pivot, and the uniform scale, all embedded in one sort of grid of 4x4 numbers, so 16 numbers. Okay. Right, so now we're going to move on, and I'm going to show you sort of, now that we've sort of spoken about what a matrix is, or kind of what's happening under the hood, let's look at how we can use it to our advantage and actually do something practical with it in 3D. Okay, so here we have a scene. And, like I said, sticking with the sort of Matrix theme, we've got our squids, and our squid is hunting down Neo. Okay, so they're trying to find him, they're trying to eliminate him. Okay, so what they need to do is find out where he is, right? So this squid kind of knows, okay, he says he's behind me and to the right, right? So he's got a lock on his position, okay? So we've got our squid who is at the center of the world. And okay, I've drawn my own grid because the other grid gets a little bit confusing as we zoom in and out. So I just want to show you that what I've got is a grid which is at the center of the world. So we're at 0, 0. And this orange squid is at the center of the world, and he's facing along the Z axis, which is usually used as basically forward. Okay, so he's essentially left at the default position where he would be, and where all your other characters would be in sort of T-pose position. Okay, and then we have Neo over here, right? Who I've made green just so that he stands out a little bit so we can kind of see. And there's this vector going from the center of the squid to the pivot center of Neo, which is at his head here. Okay, so we have a lock on his position. Now, Squiddy over here says, right, he needs some backup, right? He needs to check with his friends, and he says, okay, well, so where is he, right? Like I've got a lock on him, but let's sort of triangulate to figure out his exact location, right? Like I want some confirmation that I've spotted him, right? So he calls in an ally and says, right, so we've got this other blue guy, okay? Now our blue squid, he's not at the center of the world, right? He's not back at the sort of home base. He's moved around, right? So what I've done here is I've attached the sort of the world grid to move with our squid, just so we can kind of see that he still technically is facing the same way and oriented to his grid the exact same way, but it's just that the entire object has moved. We've translated and we've rotated. Okay. So he says to the blue guy, right? They sort of, having a conversation over over radio, and say, okay, where is he? And he says, oh, well, he's a little bit in front of me and to the left. So now our orange guy is really confused because he's like, no, but I'm pretty sure he's behind me to the right. Okay. So they both have different information about the relative position of Neo to where they are. Okay. So they're confused. So then they call in a third guy who says, they radio the purple dude and they say, okay, can you see him? And he says, yeah, he's directly above me. Like he's right above me, above my head. But you guys need to be careful because he's absolutely massive. He's huge. He's going to crush us all. But you see how the relative scale of this purple guy to Neo versus the size of these squids. Okay. Now you see I've used the word relative quite a lot here, and that's kind of one of the main purposes of, or kind of understanding matrices and what they're all about, is that it's all relative. Okay. So all of these three have different answers to where Neo is. Okay. This guy thinks he's directly above him and that he's absolutely gigantic. This guy says, well, he's in front of me to the left, and this one says he's behind me to the right. But they're all correct. And they're all correct because they keep using the word me or I. He's in front of me to the left. That is essentially saying, relative to my position and my rotation and my scale, I can tell you a piece of information about another object. So this object is in front of me to the left. He is a little bit lower than I am. Okay, I'm talking about the blue guy right now. Okay, he is about half my size and is sort of slightly facing me, but a little bit to behind me. Okay, so his rotation, his scale, and his position relative to me. But they all have different answers because they are all in different positions. Okay, so essentially they all have their own matrices, including Neo. Okay, he has his own transformation matrix. So does the purple guy, so does the blue guy, so does the orange guy. And there is a relationship between the blue matrix and the green matrix. And that relationship is essentially the difference from here to here. Okay. All right, so let's visualize these matrices, right? We keep talking about all these three different matrices, so let's actually visualize them. Now, I want to point out here very carefully, and so that there's no confusion. These lines that I've drawn here are not matrices. Okay, it is very hard, almost impossible to represent it. It's not the same as with a vector where it's just easy to represent it as a line. We have to kind of use our imagination here a little bit, but that's why I've actually represented it with this thicker line than I've been using in when we were talking about vectors, because you can just imagine that there's a bit more information, right? It's not just position offset, but it's carrying information about the rotation, the scale, the shear, the pivot, everything. Okay, but we can sort of visualize them similar to the vectors where it's this line. Okay, so all the information that it took for this blue guy to get from where the orange one was at the center of the world to where he is now is embedded in this line, let's say. Okay, and I've represented the orange one using an identity matrix, because actually you wouldn't see an orange line because this one hasn't moved away from the world center. Okay, it hasn't rotated, hasn't scaled, hasn't translated. It is in its default position. So it would be its matrix would be an identity matrix. It would look exactly like this. Okay, these numbers. Now, it doesn't help to represent these blue numbers because they would just be absolute gibberish. It just would not make any sense. It would just be a bunch of numbers. I could put 16 random numbers on here and you wouldn't even know the difference, because just, there's no ways you would know. So what I'm doing here is I'm representing it using these thicker lines. But this is going to help us talk about these matrices and kind of understand the relationship between them a little bit better. Okay. So just think of them like we've been working with the vectors, except that there's just a bit more information in there. Not only is it position, it's also all these other attributes. Okay. Now, just like with vectors, we can calculate the difference from one to another. So temporarily, and just to kind of not confuse things, I'm going to switch off the purple guy and we're going to look at the one at a time. Okay, so blue says, right, hang on. He's in front of me to the left and a little bit down, and he's facing this way. He's got a bunch of information about the relationship between green and himself. Okay, so what we can do is essentially very similar to how we do vector maths. We want to calculate the difference. So in other words, this red line is what the matrix we want to calculate. And remember, when we were doing vectors, we said we can calculate the difference from one vector to another through subtraction. Well, you can essentially do the same with matrices, but there are a few extra steps just because of the amount of extra information. So I'm going to switch this on and we're going to examine here just the calculation. Now, it's important to understand that with matrices, it is kind of one generation more complex. So everything that you would do with a vector, where you would add vectors, instead of adding them, you multiply. Okay, so addition becomes multiplication. When you multiply two vectors matrices together, you're essentially adding them both. So if the one is, it's like if I say to you, walk 2 steps forward, turn to the right, then go 1 more step forward. So in other words, you've moved in kind of like an L shape, right? Like a knight on a chessboard. Okay, 2 forward, turn right, and then move 1 more forward. If that information was embedded in this green matrix, and then the blue matrix was take one step forward, turn left, and then another step forward? Well, to essentially end up in the resultant position of doing both of those movements. So you now move 2 forward, turn right, 1 forward, then another forward because of this one, and then turn left and another one, right? So all of that information added together, if you multiplied these two matrices by one another, you'd end up in that exact same position. So it's sort of just a long way of explaining that multiplication is how you add two matrices together. In the same way that you would want to add two vectors to get a resultant vector, you multiply matrices to get a resultant matrix. Okay, and then it's the same with subtraction. To calculate the difference between two matrices, you need to divide. With vectors, we subtract to get the difference, but subtraction becomes division, addition becomes multiplication. But remember that we already early in this tutorial, we explained that multiplication and division have a relationship, and that is that division is actually multiplication, but with an inverted number. And invert works on matrices in the same way that it works on vectors. Now, like you can invert a number, so you just essentially reverse the direction. So that's whether it's just a single number, which remember is actually just a one-dimensional vector, or if it's a vector, then inverting it reverses it, essentially just changes the direction. Well, with a matrix, when you invert it, it inverts everything. So all of the scaling becomes the opposite. So scaling to, maybe up by 2, so in other words, double the size, becomes 0.5, so half. Any rotations reverse, all the shearing reverses. It essentially does a lot of work for you when you just invert a matrix, okay? So we can then, if we have simple multiplication, we can multiply one matrix by another to get the sort of result of both of them. And if we want the difference between two, we multiply them but simply invert the second one. Okay, so really simple, and based on the principles we've already learned about maths, it's just that you need to remember that with matrices it goes one generation higher. So addition becomes multiplication and subtraction becomes division, and that's all you need to remember. Okay. So now I'm going to switch that off, and we're going to have a look at this. So we want to figure out the difference between basically green and blue, to figure out this difference. And so we take the green, then we invert the blue, and we multiply them by one another, because we essentially want to add them, because adding one that's been inverted means subtraction. So we're calculating the difference here. Okay, I hope you're following with that kind of logic, right? So if I do that, if I take the green one and multiply it by the inverted blue, then this is what happens. So let's switch them on, and that's where the green ends up. Now why? What has actually happened here? At first, this might seem a little bit random and make no sense. But let's imagine we're looking through the eyes of this blue guy. Okay, so we are him, right? And we say, okay, well, so where is Neo? So he looks to his left and goes, oh man, there he is. He's just a little bit in front of me, and to the left and a little bit down. Okay, and he's kind of facing in my direction, but a little bit behind me as well. Okay, so that's his information. Now, if we imagined that he was at the center of the world instead of where he is now. So he's not at the center, but let's say to him he is. He's at his own center of the universe. You can never get away from yourself. You're always at the center of your own universe, okay? Things are always in relation to where you are. Something is on your left, but it could be on someone else's right because they're facing a different way. And so if we imagine that this was the center of the world, then that's where Neo would be. Well, if we now go to the orange guy who is at the center of the world, okay, so he is in world space, and we now look a little bit to the left and down, well, we see Neo in exactly the same position, as he was relative to the blue guy. So ultimately what we've done by calculating the difference matrix here, so in other words the red line, okay, by subtracting these two. And how do we subtract? We divide. And how do we divide? We multiply but invert the second one. By doing so, we've calculated this red matrix, which is essentially the difference between blue and green. And that then means that it gives us green relative to the center of the world. Okay, because it's to the center of the blue guy's world, who is at the center of his own universe, right? So if I show you here, if I blend, I've essentially, I'm blending away those transformations that the blue guy has. All of his rotation, his scale, his translation is all being reversed. And you'll see there that when we do so, Neo, who was to his left and forward a little bit and down, once we remove all of those translations, lines up perfectly with the transformed version of him. Okay, so that's the one that we're calculating based on reversing the matrix. Well, here, when we reverse all the transformations, you see that he lines up perfectly, and that our blue guy lines up perfectly with the orange. So when he is at the center of the world, then Neo is here. But when he is transformed and essentially in his own matrix, then Neo is here. But relative to him, nothing has changed. You know, as far as you're concerned, while this is all happening, while we're blending here, if you had to ask him, is Neo moving? He'd say no. Because he's moving, but so is Neo. They're moving equally relative to one another. And so nothing's happening except we're reversing the matrix between these two. Okay, so let's have a look at another example of the purple guy. Just do the exact same thing, just so that we know we understand. Okay, so we want to calculate the difference between these two. So we say, okay, we're going to go from the purple guy, where is the green, right? So then you need to, because this is from and that's to, you reverse the from. So we want to say this one, green, minus purple. How do we do subtraction? We divide, because it's matrices. And how do we divide? We multiply, but invert the second one. And remember, we said it was green minus purple, so it's green divided by purple, which means it's green multiplied by inverted purple. So that's the maths that's happening. Okay, and that's exactly what's happening in the VOP to calculate this, right? I'm literally just inverting the second matrix and multiplying them. That's as simple as that. And what happens when we do this is that result. Okay, so again, this looks a bit odd straight away. You think like, whoa, something weird has happened. But this is actually essentially what the purple guy is seeing. According to him, this is what he's experiencing. Okay, in his world, he's small. Okay, he's a lot smaller than the other ones, and so when he looks at Neo, he goes, "Whoa, he's huge." I mean, okay, look at how huge Neo is. He's been hitting the gym, but besides that, physically, his actual stature, his actual size, is huge compared to this purple guy. And also, see, the purple guy, he's at an angle. So when he looks up, as in above his own head, he sees Neo. And in fact, he sees him in such a way that it looks like if this was gravity, if this was the direction of gravity, and gravity was turned on, Neo would fall directly on him, probably landing kind of like feet and knees first and then head. So he'd probably get absolutely crushed by Neo's knee. Okay. Well, when we reverse the matrix here, then if the orange guy is essentially seeing through the purple one's perspective. In other words, at the center of the world, we now get to see what is happening relative to the purple guy's world, which is that way above us and much larger than us, we have Neo. Okay, and if he fell, if gravity was turned on, normal gravity, as in directly up and down now, he would fall, probably landing, almost on us, not quite, but, he'd be landing on us and landing knees first and then face. Okay? So it's essentially exactly what's happening here, but just with the purple matrix reversed. So you can see here, I blend and take the purple matrix back to where it was. So scale it back up to what it should be, so that he's the same size as all the normal squids, and undo all of the rotation and all of the translation, and you'll see that his line of sight, this red line, is still pointing exactly to Neo's head, which it was over here. So you can kind of see here visually what's happening when we reverse a matrix. And the reason for reversing it is ultimately to just say what is this object in relation to this object. Okay. Now we can do lots of cool things with this. With this information, we can reverse matrices because maybe this purple guy's moving. And if he's moving, it means his matrix is changing every frame. So he's got a different set of 16 numbers every frame. But if we reverse the matrix, then his matrix values on the current frame get reversed, so he goes back to the origin. On the next frame, he moves, but his numbers that get reversed have also changed by the inverse amount, and so he actually gets frozen at the origin. It's kind of like a way of moving something back to the origin and removing all animation from it. And this can be very useful when we come across things like when you want to maybe simulate something, like for example on a top of a moving train. So you've got some characters fighting on top of a moving train, and one of them jumps, and when he jumps, he sort of has maybe like a magical trail behind him. Maybe he's on fire or something, okay? You may want that to be moving relative to the world, okay? So because the train is moving really fast, then the sort of streaks of flame would be really, really long. And that would be kind of realistic, sure, but maybe it just looks a bit odd from camera. So what you want to do a lot of the times, we do this a lot of the time when doing effects, is we need to actually reverse the movement of the train, essentially nullifying all of the train's movements. So now, sure, the character jumps forward, but because the train's moving at like 100 kilometers an hour and our character jumps forward at 1 kilometer an hour, we don't want the velocity to be 101 kilometers an hour. We want it to just be 1. Okay, so what we do is we take the train's matrix and we reverse it and apply that reversed, that inverted matrix to the character. So now the character is at the origin, not moving along with the train. And when he jumps forward, he just moves forward by 1 meter. And so we can simulate the magic or the fire or whatever we're doing. We can simulate it at the origin. And then when we're ready and the simulation is all done, we take the train's original matrix, not the inverted one, and we apply that to the magic, the simulation, whatever we've done. And it will put it back where the train is, essentially now moving at 100 kilometers an hour along this direction that the train is moving. And it doesn't need to be linear. It could be, the train tracks could be snaking in a big S or going around in a big circle. It doesn't matter, because all of that information, the scale, the rotation, the translation, the shear, the pivot, everything is applied to our simulation that we did at the origin. And so the magic moves along with the train, but our velocity is calculated correctly at 1 kilometer an hour instead of 101 kilometers an hour. Okay. And so we often do that whether we're trying to cheat things so that, because maybe realistically it actually looks a bit odd, so we cheat it a bit. Or sometimes, like on an airplane, for example, when something moves, if the airplane is moving really fast, but you throw a ball up, it doesn't end up right at the back of the plane, because the plane's moving forward, because it's already moving forward relative, and there's also air pressure and everything. So basically, the internal environment of the airplane remains the same. So you would use this system to reverse the matrix, do a simulation, and then apply the matrix again. And essentially, it's like you've simulated it on a static plane. Doesn't matter that the plane's moving. It could be tipping upside down. Doesn't matter. Okay. So this is a very practical use for matrices. So we can just reverse things and know how things are in relation to one another. For example, I mean, we could even ask where the purple guy is in relation to the blue. Well, then you just take blue minus the inverted purple, well, so multiplied by the inverted purple. And now we would know the sort of relative scale and position of purple to blue. Okay, so all kind of very, very useful and fascinating. Matrices are something that I think a lot of people try to avoid because it does get quite complicated. But seeing it this way, you can see how it's almost like our vector maths. That was pretty basic, right? It's not that complicated, but unfortunately, it just kind of gets a bad reputation and then people avoid it. Now, I want to move on to talking about just one final thing, which is understanding what's kind of going on inside of a matrix and how to work with it. Because it's all fine and well understanding the maths and the practice of what it's doing, but then how do you calculate it? And as I've said before, this is not a very long-winded tutorial on VEX and VOPs, and we could talk about this for hours, and I would have to show you all the 50 different ways there are of calculating matrices. There's different nodes, there's different functions, there's different ways of doing it. But instead, I want to leave you with just a few simple ways to work with them. And then if you want to learn more, then you can obviously do something like the VEX course, or there's much more information that we can go into. Okay, but to keep this nice and short and succinct, and we're talking about just the maths of what's happening, to try and help you understand it better, I want to just show you kind of what we're doing, and then I'm going to show you an example of how to work with it in VOPs. Okay, so we look at our 4x4 matrix over here. Now, really, the difference between a 4x4 matrix and a 3x3 is that the 4x4 has translations included in it. Okay, so if we calculate only a rotation matrix, it is a 3x3 matrix. It is not a 4x4 by default. Okay, now we can make it a 4x4, but ultimately what we're doing when we make a rotation matrix into a 4x4 matrix is we're just simply adding identity translations. So we're multiplying by an identity translate matrix, okay, which would be exactly this. So here's our 4x4 matrix, which is translate, rotate, scale, and shear. Okay, but actually this is made up of a translation matrix, which is a 4x4 matrix, added to, and now remember, when we say add, I actually mean multiplied by, because they're matrices. So multiplied by our 3x3 matrix, which contains the other three, rotate, scale, and shear. Now, why these three are all together, remember I showed you earlier how shear kind of adds up to rotate. Well, shear and scale work together to form rotations. Okay, so that's why these all kind of work together. All right, so in these 9 numbers, we now have the rotation, scale, and shear added in. And this can be broken down even further into rotate, scale, and shear matrices, which are all added together. And by added, I of course mean multiplied by one another. Okay. Now, what this actually means, you'll see that when we go down to rotate, we don't lose any numbers. We don't go down to just one row. Okay. It is still a 3x3 matrix. It's not like just the top row, for example, is rotate. And so now we literally have just 3 numbers. No, we still have 9. But when we have a rotation matrix only, it is essentially the rotations multiplied by identity scale and identity shear. So in other words, just the rotation amounts multiplied by then the default values, which means nothing kind of changes. So that's how you end up still with 9 numbers, but these 3, like these 2, so the scale and shear, are sort of removed from it. Now you can also get a scale matrix, and it's still a 3 by 3, so it's 9 numbers. But these scale numbers are then removed from the rotate and shear because the rotate values are just left at default and the shear values are left at default. And then it's the same thing with our shear matrix. Okay, and so you can multiply these by one another if you want to add them together. So for example, let's say we don't have any shear values, so because a lot of the time you don't. I'll show you in our VOP example, but we do not have a shear. Shear is generally just a part of how matrices are calculated, but we generally don't actually calculate shear as its own thing because nobody really wants to shear something. Okay, you want to rotate and you want to scale. Okay, but shear is just part of how rotate happens. So we kind of need it, but only internally. So what we can do is we can calculate a scale matrix on its own. So we know just the amount of scaling that we want to apply to a certain character. And we also calculate the rotations. Maybe like you saw earlier, we had our lookup. So we can use lookup to calculate a 3 by 3 rotation matrix. And then we have our scale values. We multiply them together to get our rotate, scale, and shear 3 by 3 matrix. And then when we multiply that by our translation matrix, which is a 4 by 4, but it's a 4 by 4, but actually with the scale, shear, and rotate values set to identity. And then it'll have its own translation values. And when we multiply these together, then we get a 4 by 4 matrix, which includes all of these aspects to it. Okay, so I hope that is a little bit clear. I know it can get a little confusing, but you don't have to do this manually. It's just really good to understand kind of what's happening. And then now you'll see how this all comes together inside of VOPs just now. So remember we had this, when we spoke about quaternions, we had this calculation where I said you can use the lookat function, or there is a lookat node in VOPs to calculate a rotation matrix. Okay, so it's a 3 by 3 matrix. We feed it 3 vectors, so a from, a to, and an up, and we calculate this rotation matrix. Now this over here is only this. Yes, it's a 3 by 3 matrix, but all of the scale values, their proportions are left at default. So if you applied that matrix, you would get rotations, but you would get no scaling because scaling is set to 1. Okay, so this only returns a rotation matrix. Right, so I just wanted to relate this back. Remember, obviously, we had a final step when we had this and we were working with quaternions, was to convert it from a matrix to a quaternion because, you know, our orient is actually a quaternion, not a matrix. So we just want to essentially strip out the scale and shear from it, store it as 4 values as an orient, and then use that. Now, that is fine. But in this case, if we want to calculate a full matrix, and I'll show you how to do that now, we just don't do this last step. We already use the lookat function, and we already have a 3 by 3 matrix. But what we do need to do is add scale in, and then add translations in order to get our transformation matrix, which is essentially everything combined. Okay, so let's dive in, and we're gonna have a look at this. Okay, so hold on. So I'm going to dive inside of this node, and here we have a cube. Okay, just a simple cube, basic cube, default, right? But also what I'm doing is I'm peaking, so I'm sort of scaling up just the position of these points by a little bit, and I'm setting this to a template. So we can actually see 2 boxes on top of one another, right? If these boxes separate at all, then it means we've gone wrong somewhere. We haven't done the calculation correctly. Because what I'm doing is that the one that I'm peaking, so just this wireframe box around the outside, has these transformations. So I'm just putting it through a transform node, which has all of the sort of inputs that we would expect. And it's calculating a matrix for us and essentially offsetting this, like it's transforming this box, okay? So the wireframe box on the outside. The solid box on the inside, however, is being controlled by this VOP. And inside of this VOP, I'm recreating what is happening in this transform node. And so we can kind of see if, as long as whenever we translate, we rotate, we scale, or maybe scale non-uniformly, so on 1, and we can do uniform scale, and we can rotate again, and everything still stays exactly the same. Okay, you'll see that these always line up no matter what I do to these values, and this is because I'm recreating it inside of here. So let's dive inside. Now, again, I've said before, this is not a lesson on VOPs. So if you're newer to VOPs, just understand that this is kind of going to be a little bit confusing. But even if you do know VOPs, this can look a bit much. I want to point out that you very rarely are going to recreate a full matrix like this. There's no point. Just drop down one node, the transform node, and use it. Okay, use what there is. The reason I'm recreating it here is to show you how you can recreate each component. So if you wanted to keep one but maybe just change another, you could do it through VOPs. Okay, and it will also show you how to apply things in VOPs. Okay, so like I'm saying, don't get overwhelmed by this. You are not expected to ever really create a full transformation matrix, because if you are doing the whole thing, you would just do it through one node. Right, so let's dive inside and have a look here. Now, one thing I want to point out, when we look at our transform node, there's a bit of extra information here. Not only do we have our translate, rotate, scale, and uniform scale, but we also have this transform order. So you see here it says scale, rotate, translate. And then our order here, our rotation order, is X, Y, and Z. This is a bit of extra information that is also embedded inside our matrix. And this is very important for a matrix to work. Okay? When we invert a matrix, it reverses this order as well. So it's really good to know how that inversion works. And if we've done it in the wrong order, then when we invert it, it's also going to be in the wrong order. So, okay. So keeping that order in mind, let's have a look at these and examine them one at a time. Okay. So what I've got here is a scale matrix. All I'm doing is calculating a scale matrix. If I hover over here, you see this scaled matrix, and it's a matrix 3. So this is the matrix 3. It's got 9 numbers, okay, 3 by 3, but everything else is zeroed out to default except for the scaling. So how I get this is I'm calculating an identity matrix. So what I did is I used a constant node. It's a float, 9 floats, so it's a 3 by 3 matrix. And it's set to default, so 1, 1, 1 on the diagonals. Okay, this is an identity 3 by 3 matrix. And then there's a scale node. So all this is doing is scaling a matrix by a number, so by a vector, which is essentially saying this is a way of taking a human readable input of a certain scale that we want to give it. So we're used to scale being an XYZ thing, like here. X, Y, Z scale. And it allows us to give it that scale, and it will scale these 9 values according to those 3 values coming in, right? And that's all I'm doing, is I have a constant where I have scale, but what I'm doing is I've got these 3 numbers linked to the same 3 numbers over here. Okay, so when we set this to be 1.5, then when we come in here, you'll see this is 1.5. Okay, so it's exactly the same, but I'm also just multiplying by a float. Okay, and that float is my uniform scale. So now you can see how these two interact. They don't actually interact inside of the matrix. They are done outside, multiplied by one another, and then added into the matrix. Now, when they're multiplied, this is something I mentioned to you before, be very careful of the order. Although multiplication of vectors doesn't matter, and a float is just a one-dimensional vector, what does matter in Houdini is the fact that the first input determines the type of the output. And because we want a vector here with all 3 numbers, we make sure that the float is multiplied second. If we reverse this, then the type will be float, which means that the outcome is float, so it compresses it to only one value, and therefore our scale is wrong. Okay, you can see there that the scale is very wrong. If I reverse that again, so it is a vector coming in multiplied by a float, then that's a vector coming out, because of the input and output are both vectors, so now it works. Okay, so this is how we calculate a very simple scale matrix. We can feed it 3 numbers, x, y, z scale, and a uniform scale, and what it returns is a 3x3 matrix that only has scale. Okay, now let's look at rotation. Very similar idea. We have an identity matrix, exactly the same identity matrix in fact, but we have a rotate node. Now the rotate lets us rotate a matrix by an axis and an angle. Now, I mentioned to you before when we spoke about quaternions that there are different, there's Euler, and there's axis and angle, and then there is quaternion rotation. Okay. Now the rotate wants it in the format of axis and angle. So in order to get axis and angle, we're just using a quaternion to vector, right? But if you go in and hit tab, you'll see that quaternion to axis/angle is the option. Okay, but when you drop it down, it's not called that. It doesn't have the same name. It is called, it calls it quat to vec, but really it is quaternion to angle axis. Okay, and what this does is it returns one vector, but that vector's normalized vector is the axis, and then the length of it is the angle. Okay, so remember we worked with normalizing and length before, and now you see how it comes into practice. The normalized vector, so in other words, the direction of this vector is what we're using as to determine the axis, but it's storing, instead of us giving us literally a vector and a float, it's just being efficient by giving us just one vector, because it knows that the vector we need is normalized anyway. So it's using the length component to store the angle that we rotate around that axis. Okay, so if we do this quat to vec, the resulting vector here is kind of useless in any other form other than going into a rotation matrix. Okay, because it's kind of this, we need to normalize it and take the length and feed it in like this. Okay, and so this method over here is a way of converting from axis angle, which is one form of rotation, to quaternions, which is another form. Now, again, I've said to you before, quaternions are not numbers that we like to look at and input. They, just like matrices, are impossible to work with and very tricky. So instead of working with that quaternion, we are going to do one more level of conversion, which is to convert from Euler to quaternion. Okay, so you'll see here if you type EUL, there is Euler to quaternion. Okay, very simple. And all it does is it takes 2 inputs. It takes our Euler rotation, which will be 3, which is now what we're used to seeing. Okay, X, Y, Z, right? That's what we're used to seeing. But it also takes sort of an option, right? It's just a Boolean kind of an integer option of which rotation order. Now remember I said the rotation order is important, and it is even present when we do our normal transform. It's over here. So this option here is just determining what happens here. And of course the default is XYZ. Okay, and we're creating a normal matrix rotation here, so it's just XYZ. You can leave this at default, but just so you understand what this is. Okay. Now, you'll notice one other thing here. It says rotate, but in brackets it says radians. Now, again, we've worked with radians before, and we know that there's just a direct conversion from degrees to radians. But when we say to something to rotate 90, we mean 90 degrees, not 90 radians. Nobody uses radians. So we do our degrees to radians node. Okay, and that just converts incoming degrees to then outgoing radians, which means that we can feed the radians into the Euler rotation because it wants radians. But what we get to feed it is degrees. And this now makes sense to us. So I know this is kind of a confusing chain, but really I wanted to work it backwards from the end so that you can see the logic behind it. But really what we're doing is we're taking 3 degrees, right? So it's XYZ in degrees, which we're used to working with. Converting them to radians, feeding the radians into an Euler to quaternion, choosing the rotation order, and now we have a quaternion. We convert that quaternion into an angle and axis, which is the length of which determines the angle, and the normalized vector determines the axis. And we feed that in to rotate our identity matrix. So essentially we're taking something that's blank, like a blank empty sheet here, and applying these rotations to it in order to get this this matrix that comes out is an R matrix. In other words, a rotated matrix. Okay. So you see here we had a scale matrix. Now we've got a rotation matrix, and then we need our last one, which is translation. Okay. And then we'll talk about how we combine them. So fortunately, the translation one is really simple. The only difference here is that we need a 4x4 matrix, because remember, 4x4 stores translation, 3x3 does not. So if we created an identity matrix that was 3x3, we wouldn't be able to translate it because we can't store those in the matrix. Okay, it uses the extra numbers to store translation. And then we just take our translation values and feed it into the translate node. So you'll see there's a translate, a rotate, and a scale node, which all work with matrices, but the scale and rotate work with 3x3 matrices. The translate works with 4. And that's all we do. Okay. But now we need to combine these. And here is a hint at how we need to combine them. Scale, rotate, translate. That order is important. Okay. And as I said before, to add things together, if there are matrices, we multiply. So scale, rotate, translate. We take scale multiplied by rotate. This order is important. If we reverse this, it changes. Look at how that now no longer lines up, and there's some shearing happening. It's away from the corner over here, and this is penetrating. If I reverse it again, you'll see it goes back to normal. Okay, so look at that difference. That's because of rotation order, and it matters. Okay, transform order. So scale, rotate, then transform. But after scale and rotate are combined, we still have a 3x3 matrix. What we need to do is change it to be a 4x4 matrix. Because what we would like to do, the easier way would be if we use Houdini's, sort of the way Houdini works, so the convention, which is that the first input determines the output. So we say we'll put translation in first so that we have a 4x4 matrix, and then we just put our 3x3 matrix in, and it'll convert it automatically to 4x4. This sounds like a good idea, except for the fact that, remember I said this order matters, and so now we've had to go translate first, then scale, then rotate. Okay, and so this doesn't work. Even though this is what we want a 4x4 matrix, this order is important as well to us. So what we have to do before doing that is convert from a matrix 3 to a matrix 4 so that the type is correct, so that there are empty spaces where this information can be stored. So now, because our input is in matrix 4, the output will also be a matrix 4, and then we put translate in a second input so that we have gone scale, rotate, translate. Okay. And then the way that we apply this matrix. So this matrix over here is exactly what we want. Okay. This is those 16 numbers that determine the position of this. Okay. But in order to apply that, we can just multiply our point position. Okay. Now, when you do a multiplication of a matrix, what you do is you keep the first input, so you make sure, because what we want is the resulting point position. So it's vector multiplied, so vector goes in first, and you simply multiply that position by the matrix. Keeping in mind that point position determines scale, translate, and rotate, because if you move these points of the box further away from one another, it looks like the box has scaled up. If you move them closer to one another, it looks like they've scaled down. If you move them all 3 units to the left, it looks like the box has translated to the left. If you move this one closer to us, this one to the left, this one further away from us, this one to the right, then it's going to look like the box is rotated. So point position, even though it's just one vector, can actually result in all of the translate, rotate, and scale. And so that's why a 4x4 matrix can be multiplied by our point position. Okay. But this only works if we have an unpacked geometry. So if we're literally working with a bunch of points. If we do have packed geometry, then instead we need to transform it in multiple ways. You can either use a transform node, or you can write to the primitive intrinsics. So that's getting very complicated, and so that's outside the scope of this course because it gets a little bit complex. But ultimately, we can create a matrix in the right order here, manipulate these numbers in any way we want, and then multiply them by a point position, and then we get the result. Now, I just want to show you one quick thing. I'm just going to create a custom attribute and call it MTX, and it's a matrix just to write out the matrix of these points and then show you in the geometry spreadsheet here what our matrix looks like. Now, it is obviously very hard to see. In fact, I'll get rid of our point position. It's a bit hard to see because there's 16 of them. But you see all of these numbers determine all of that rotation, translation, and scaling. Okay. And almost impossible, like I said, to work with directly, and yet we can convert from one to the other. And you'll see, by the way, just so you know, it says 15, but that's because the first one is numbered 0. So there are 16 of them. Okay. Right, so that just sort of shows you how the matrix can be applied. And you may want to do this because, for example, like let's say you want to create a rotation matrix. You can rotate something, and then, for example, because we know there's a step here where we have a quaternion before we convert it back to axis and angle. So if we had 2 different rotations, maybe, okay, so we've got our box here, and then maybe we create a second rotation. So let me just take this one and I'll break it and say, let's do some different rotations, okay? So I've got some rotation here, and then I've got the one that's reading from the transforms. We can now use our spherical linear interpolation node because we have 2 quaternions. It's nice and smooth rotation blending. Okay, so we can go with this bias from the one to the other, and we can rotate nicely from one to the other. Okay, because we now have a quaternion, we know that this will be a spherical linear interpolation instead of if we blended just between these degrees, then it might be fine, but sometimes you'll get flipping, like you'll get sort of where things go through one another. So here we would do a mix node. So in VOPs it's called a mix, but it is actually applying a lerp function, so the linear interpolation function. Okay, and if we plug in 2 vectors, then it reads the vector, and you'll see here we can do the same thing. We can blend from the one to the other. In this case, it seems to work okay, but if we maybe went more extreme with these rotations, then you'd start having a few issues, and things might flip on top of one another or do some kind of weird results. Okay, whereas for that same result, the spherical linear interpolation is going to take just the shortest path to rotate from one to the other. And so it won't do all of those tumbling and spinning. It literally just finds the shortest way to rotate from A to B. Okay, which is very useful to know how to do this, because sometimes you literally want to do a blend shape, but the blend shape goes through one another. If you just blend it, it just kind of crushes and compresses and then expands into the new shape. And that's not nice. Whereas if we do a spherical linear interpolation, we can literally have it tumble into correct position and it maintains its volume. So there are lots of cool things we can do, and I wanted to show you this example because it combines a lot of what we've learned in this tutorial. Length and normalizing, quaternions and vectors, matrices, identity, rotation, scale, all of it, right? Spherical linear interpolation, which is called mix. We use radians and sort of the degrees to radians rotation, Euler rotations, and then multiplication, but where order does matter, and then sometimes where order doesn't matter. So this kind of shows you just all of the different things that you can do with maths in Houdini.